Uh, Good evening, everybody. Our project is multi-robot map merging with the code MuRo. With our teammates are Kashif, Abhishek, and myself, Piyush. Um, so to give a context, when it comes to any, let's say, warehouse environment, if you have to deploy any autonomous robots over there, we firstly map the entire environment using lidars, and once it is mapped, the robot knows where it is in the particular environment. And usually, what we do is we use one robot, we take it from one end of the place to the other end, and it maps the entire place. But what if the place that you're mapping is very huge, and what if you have more than one robot at your disposal? Can you speed up this process? And that is what we are trying to do in this particular project. In this particular project, we are trying to use more than one robot, in our case, two robots, to map a particular environment. Um, and each robot creates its own local map, and those two local maps are combined into a global map. So key features of our project include, number one is we have implemented an algorithm which makes the robots navigate autonomously and map. And second is we combine both of the maps into one global map. Tools used. We have used C++17, and we have used ROS2 Humble. For the simulation, we did not go with Gazebo. We instead went with NVIDIA Isaac Sim, because it is the future of simulation. And few other packages that we used was Slam Toolbox for the mapping, Nav2 for autonomous navigation. We used OpenCV for image processing, and RViz for visualization.
Thank you, Piyush. So as explained by Piyush, we saw that there was one autonomous package responsible for getting the robots navigate through those complex environment. So the first image you basically saw here in this slide is the environment that we work with. This whole was built right from scratch. This is Isaac Sim. You can see the two robots at the end of this room with all the cluttered environment. So the frontier exploration, which was responsible for navigating the robots through the dynamic obstacles, including the walking human, and it was when the robot was navigating, the maps of the individual robots were being formed, and each time we had the RViz for the visualization and the map expansion. So as the robot was navigating through the environment, those individual maps were automatically aligned. Why? Because in the next half, you will see the map merger, which is merging the two maps together. So in order to have the common features between those two maps, it was necessary to have one central line between those two, which will align the two maps in one uniform way. And the next was navigation system. So after the map was merged and we had the unified map, the task was to navigate through the map, because that would validate the whole point, right? The next integration features included the ROS messages, interfaces, services, the whole coordination system, including behavior trees, and of course the performance and monitoring logs while the whole system was running. This architecture explained what exactly the whole flow of the project was. It combines of different blocks, like the environment understanding, that was Isaac Sim, having Slam running on it, and the waypoint manager, which was behavior trees in this case. The next is the mapping system, which included the frontier exploration and the Slam toolbox. As the robot moves, the sensors from the robots, usually the 3D lidars, scan the whole data, and the package also included the conversion of 3D to 2D in order to have the RViz visualization done. And as you can see, those sensor data are reaching back to the Slam toolbox. And once those mapping is completed, we see the blue box as waypoint manager is now feeding signals to behavior trees, which is governing the whole navigation system here. Yeah, Abhishek, please.
Yeah, so in this project, we successfully implemented multi-robot SLAM. So basically, we created entire algorithm from scratch called as on the basis of frontier exploration. And with that, after that algorithm, we were able to get all the necessary lidar points we need for the map merging. So for the map merger technique, what we did, like both of the robot explored the entire map separately, and once there was a common ground between them, the algorithm stopped, and then image processing techniques were used to later on merge the maps, which definitely avoided single point of failure, which happens in traditional techniques. And for seeing performance metrics, we were able to do real-time obstacle avoidance, and the map merging also happened real-time. So in the next slide, we'll be able to see the result properly. Yeah, so also talk about deliverables. So we followed agile methodology and TDD properly. We had routine meetings, and we also did all the commits as they were decided during sprint planning and backlog. We were able to pass all the unit test, and code coverage was up to 97%. You can see the commits, routine commits we did. Okay, so let's go to demonstration now. So in the map, you can see both the robots are exploring individually using Frontier Explorer, and simultaneously both the maps are getting created separately.
This can be this can take a while, so we can maybe skip to the other
Yeah.
part where the map is being actually merged.
Yeah. So yeah. So we got separate maps and a common ground. So after that, once we run our image processing pipeline, you can see we created a single map from that both image separate maps. Kashif will explain the next video.
Yeah, so in the next video, we have that map being utilized for the navigation. As you can see, each individual robot will be navigating using the map. Here we were using the stack of nav2 for navigation. The robot has different waypoints. Like in case of warehouse, we have different systems at different blocks. One of them could be manufacturing, the other could be assembly, the other could be unloading. So those navigation points were decided through the Arvis AMCL, and those points were one by one navigated through the robot, as you can see in the video. As the arm robot, you can assume that that would be responsible for assembling, and the robot now navigating back to the unloading place. Once the whole navigation is completed, it then traces back the same navigation points and reaches back to the position where it was initially at stall. The right side window explains the whole Arvis, where you have AMCL in action, local cost map and the global cost map working together and responsible for the whole navigation here. So as you also see, the future plan for this would be now including 3 different robots, not only 2, and getting the arm in action. Hopefully, we should be able to get it completed as an ambitious project this winter break. So now as you see, the robot is getting back to its original position, and it will further rest ahead. So that's all, folks, for the project. Thank you so much.